Managing one's wealth is an intrinsic skill required in modern times due to the financial stress placed on people and businesses as a result of high inflation rates and the global increased cost of living. The use of reinforcement learning has shown great potential in managing portfolios, successfully mitigating risk and providing favorable returns on investment. This field has the potential to be used globally in the pursuit of protecting an investor's wealth, providing safe growth of their assets, as well as mitigating the risk of falling into poverty. We investigate the performance of an algorithm with great promise in this field in an analysis of the twin-delayed deep deterministic policy gradient algorithm for portfolio selection by Nicholas Bard, Terence Van Sale, and Andrew Pascaramudi. State-of-the-art reinforcement learning algorithms have shown suboptimal performance in some market conditions with regard to the portfolio selection problem. The reason for suboptimal performance could be due to the overestimation bias in actor-critic methods through the use of neural networks as the function approximator, resulting in a suboptimal policy being learned by the agents, hindering performance. This research focuses on using the twin-delayed deep deterministic policy gradients or TD3 algorithm for portfolio selection in order to achieve greater results than previously achieved. To determine the robustness of the TD3 algorithm, an analysis of the overall performance and effectiveness of the algorithm in various market conditions is conducted. Fujimoto et al. Proposed an adaptation to the deep deterministic policy gradients to create the TD3 algorithm. In this paper, the authors proposed a new algorithm in an attempt to address two issues in actor-critic methods, namely the overestimation bias as well as variance within the temporal difference updates of the neural networks. The authors propose clipped double Q learning in order to reduce the overestimation bias. This is an extension from double Q learning in which a pair of independent critic networks are used for independent actor networks to make value estimates and are updated separately. Clipped double Q learning uses the minimum of two value function estimates, which mitigates any additional overestimation by the value target. A TD error can be found in each temporal difference update due to the Bellman equation never being completely satisfied. These errors from the updates can accumulate and lead to suboptimal policy updates and are another source of overestimation bias. The authors propose delaying the updates of the target networks until the error in the value function can become as small as possible. This allows for more stable updates to the policy, decreasing the chance of TD error affecting the learned policy. This is done by only updating the target networks after a certain number of update steps. The update to the target networks is also done at a slow rate in order to avoid variance affecting the learned policy. With these two main issues addressed in the TD3, there is promise for the algorithm to achieve greater performance than its predecessor, the DDPG, as well as other state-of-the-art algorithms within the portfolio selection problem. These algorithmic changes have the potential for the agent to be more consistent across markets and produce more reliable results. Following the framework set out by Jiang et al., we create a portfolio selection reinforcement learning environment for us to train, test, and evaluate the TD3. In order to analyze the performance of the TD3, we also implemented the DDPG, DDQN, and PG algorithms. This provided us with a fair comparison across different model-free reinforcement learning methods. For the experimentation of this research, we collected price data from the 5 markets, namely Johannesburg, New York, Tokyo, London, and Sao Paulo stock exchanges from the 1st of January 2010 to the 31st of December 2019. We select 6 stocks at random from the top 25 assets in the market based on market capitalization. These 5 markets resemble a variety of market conditions for the agents to be trained on and provide insight into the performance of the agents in different market conditions. All agents were trained on all 5 markets from the 1st of January 2010 to the 31st of December 2014. The agents were backtested on each market from the 1st of January 2017 to the 31st of December 2019. The evaluation criteria used in this experimentation to measure the performance of the algorithms were the Sharpe ratio, annualized rate of return, final portfolio value, and maximum drawdown. With the Sharpe ratio being the main evaluation metric for portfolio selection due to measuring the return of the portfolio as a proportion of the standard deviation or risk of the portfolio, the results show that the TD3 agent performs best out of all the agents and baseline strategies across all markets considered. The overall performance of the TD3 agents highlights the robustness of the algorithm to be used for portfolio selection. The TD3 performs best when considering a market with high volatility. In the TSE market, the TD3 is able to achieve 4.1% greater annualized rate of return and 0.273 greater Sharpe ratio than the next best agent. Similar results are found in the SPSE, where the TD3 maximized the volatility in the market to produce a Sharpe ratio 0.11 greater than the next best. In a bull market such as the NYSE, the TD3 produces results far greater than any other algorithm or strategy, with a Sharpe ratio 0.208 greater than the next best. The NYSE is a market with less volatility compared to the SPSE, yet the TD3 still manages to achieve the best results. The TD3 struggled to achieve the best results of all of the algorithms in the JSE and the LSE markets, where the market remains relatively flat during the training period. This could be due to the agent not being able to identify strategies to maximize wealth in a relatively flat market, even in the presence of volatility. Even though the TD3 did not achieve the best results for these markets, the results achieved did not trail too far behind the best performing agent. This shows that the agent performed consistently throughout the markets compared to the other agents. This is sufficient proof that the TD3 algorithm is indeed well suited for the portfolio selection problem. Through experimentation, the TD3 agent achieved the best results across all 5 markets that were used for testing. The TD3 produces a consistent performance in various market conditions and proves to be a more robust algorithm to use in portfolio selection. The TD3 also performs better, achieving greater final portfolio value, Sharpe ratio, and annualized rate of return than its predecessor, the DDPG, in 4 of the 5 markets. This shows that the algorithmic changes made in the implementation of the TD3 have improved the policy that the agent can learn.